Hello everyone! Today I will present our work regarding a predictive auto-scaling approach for OpenStack. I worked on this topic in the context of my Ph.D. project, which I'm devoting to data-driven methods for data center operation support. As we all know, a large portion of the internet is nowadays powered by cloud computing. A key success factor of such paradigm relies on the ability of cloud providers to operate their infrastructure 24/7. Promptly addressing any sort of issue, from hardware faults to software bugs. However, given the scale and the complexity of such systems, their activities are very difficult and many things can go wrong in many different ways. Indeed, every now and then we can see some major incident hitting the news. An outage occurring in data center of a major cloud provider can propagate rather quickly and cripple a huge number of applications that depend on it. Events like this can trigger a series of undesirable chain reactions that typically result in customers experiencing all sorts of performance issues. In some cases, affected applications manage crucial aspects of organization's daily business, like granting access to email inboxes or sending important documents, and the unavailability of such services can severely slow down all activities company-wide. In other cases, a huge outage may just keep you from surfing your favorite social feed for several hours. Or again, since IoT devices are becoming more and more part of our lives, it could be impossible for you to enter your home as the smart lock on your door is blocked by a faulty service running somewhere in the cloud. Cloud computing is being more and more adopted to run applications with varying level of criticality. Therefore, service providers are required to enhance their capabilities to react quickly when disruptions happen, or better, to prevent them altogether. Cloud environments are typically managed with very advanced automated procedures, but current approaches to data center operations are still heavily human-centric and thus are susceptible to human error. The core objective of my Ph.D. project is to develop a comprehensive data-driven framework to address the problems that operations teams experience when dealing with distributed cloud environments, leveraging on the enormous amount of operational data that are available in this kind of scenarios. In this talk, I will be focusing on a fundamental property of cloud system that is one of the most important requirements for realizing resilient cloud services that can be operated proactively. Elasticity is the capability of cloud services to automatically adapt their set of allocated resources as the workload changes over time. This allows for keeping performance stable despite fluctuations of the overall aggregated traffic. As a consequence, assuming for instance a sudden growth in the workload, if a service is effectively elastic, a client should not be able to observe any notable change in the service response times. Although there are two main types of scaling, horizontal and vertical, in this work we are only concerned with horizontal scaling. So we are considering the case where an application supports being replicated across multiple instances for availability purposes, and we tune such number of instances to adapt to the current workload. This property is typically implemented by means of control loops that, based on the status of the service as reported by the monitoring system, decides which is the required action to take in order to keep the service running smoothly. Indeed, classical auto-scaling mechanisms are inherently based on reactive automation rules that scale a service whenever some metric, for instance the average CPU usage among instances, breaches a predefined threshold. In practice, to make the mechanism more stable, it is common to require the threshold to be breached for a few consecutive observations before triggering any action. Developing and tuning such rules become particularly cumbersome when scaling a service involves non-negligible times to set up additional resources, as it frequently happens in large-scale production environments. Indeed, despite the mentioned precautions, classical threshold-based control loops remain inherently damp, in the sense that they do not account for the rich dynamic of the observed metrics. As an example, consider the CPU usage evolution depicted in this figure. A threshold-based scaling policy would treat scenarios A and B in pretty much the same way. As soon as the CPU breaches the threshold, represented by the red line, a scaling action is triggered. However, a human operator, based on their prior experience with this fictional service, could easily distinguish between scenarios A and B. While A may be ignored, it is clear that B would require urgent actions to be taken. In such cases, time series forecasting techniques can play a fundamental role in enhancing the capabilities of an elasticity controller to prevent a service from saturating its capacity. In this work, we propose a general framework for predictive operations of a cloud infrastructure. In particular, our approach enables predictive auto-scaling of cloud services based on the status in which the system is expected to evolve in the near future. We leverage on time series forecasting techniques to predict the future dynamics of key metrics, for instance, resource consumption metrics, and apply a threshold-based scaling policy on them. The result is a predictive policy that is able, for instance, to automatically anticipate peaks in the load of a cloud application and trigger appropriate scaling action ahead of time. This allows to accommodate a sudden growth in traffic without clients being affected at all. We prototyped our approach as an open source forecasting component that relies on and extends the monitoring capabilities offered by OpenStack Monasca. This results in the availability of predictive analytics that can be leveraged by orchestration components like Heat or Senlin. We also provide experimental results obtained by running our component using a linear regressor, a multi-layer perceptron, and a recurrent neural network as the underlying predictors. Their performance were then compared to a classical reactive auto-scaling policy. However, the proposed framework is extensible and allows for easy integration of customized models to realize the predicted policy. As I said, our forecasting components heavily rely on the tremendous monitoring function offered by Monasca. That is a highly scalable, full-fledged monitoring as a service solution for OpenStack, also compatible with Kubernetes. This picture captures the complexity of Monasca that follows a microservice-oriented architectural pattern. In the top right corner, you can see one of the fundamental components, that is the agent, that is deployed on every compute node to collect measurements and forward them through the Kafka bus. At the bottom, you can see the persistent layer that includes InfluxDB for storing time series data. Such data can then be consumed via Monasca API. Monasca also provides a scalable alerting pipeline based on Apache Storm that allows for setting fairly complex rules to be checked against the monitoring data and possibly send out notification to external applications. This picture shows our approach to predictive auto-scaling works. For the sake of simplicity, we assume our Elastic service to consist in a Senlin cluster of Nova VMs, although our approach is agnostic to such implementation details. As soon as new system-level measurements from the compute instances are ingested and made available through the Monasca API, we leverage on our forecasting component to predict the future dynamics of some relevant infrastructure metrics. These are assumed to be key indicators for the amount of load that the system is handling, for instance, the CPU utilizations. The underlying forecasting algorithm is fed with a time series that is obtained by aggregating the measurements of the target metric as collected from the individual VMs. The forecasts outputted by the predictor are then persisted back to Monasca, such that other components and human operators can consume them. The forecasted metric data are then evaluated by a threshold-based scaling policy. Such policies typically trigger a scaling action as soon as the specified threshold is repeatedly breached for a certain number of subsequent observations. The threshold checks are performed by the highly scalable alerting pipeline provided by Monasca through Apache Storm. Then, depending on the conditions of the system, Monasca notifies the Senlin orchestration engine regarding the scaling actions to be performed. In order to validate our approach with a setup that resembles the production environment, we also placed an Octavia load balancer in front of the Senlin cluster to evenly distribute the requests coming from our test application. Here you can find some additional details on the configuration of the infrastructure components. For the VMs, we used the Ubuntu 2004 cloud image, customized by pre-installing the dependency required to run our test application. Then we set the boundaries for the elasticity of the Senlin cluster, such that at any time there were at least 2 and at most 5 active VMs. At the beginning of our experimental runs, we made sure that current size was 2. Also, the load balancer was set to follow a round-robin policy, such that each VM could get an equal share of the incoming traffic. For what concerns the monitoring data, Monasca was set such that the CPU usage, that is the KPI we selected to assess the status of the system, was collected every minute for each individual VM. The forecasting component was configured to output a new prediction with the same interval, using the last 20 minutes worth of data as input. In particular, the input to the underlying forecasting model consisted in a time series reporting the sum of the CPU usage measurements of the currently active instances. The output of the model was the estimated value in 15 minutes of the same time series. The output was then divided by the number of currently active instances to get an estimate of the average CPU usage in 15 minutes, assuming the cluster size to remain constant, and then persisted back to Monasca. To implement the classical reactive scaling strategy, the alerting component of Monasca was set to trigger a scale-out action wherever the actual average CPU usage of the cluster breached the 80% threshold for 3 times in a row. Similarly, to implement the predictive scaling strategy, the alerting component was configured to trigger a scale-out action whenever the predicted average CPU usage of the cluster, as outputted by the forecasting component, breached the 80% threshold for 3 times in a row. In this case, we used PyTorch to implement standard flavors of the MLP and RNN, while we used the implementation of the linear regressor provided by scikit-learn. Notice that such settings impose a delay of at least 3 minutes before an action can be triggered. Also, each scaling action could adjust the size of the cluster by 1 instance only, and after that, the cluster enters a cooldown period of 20 minutes. We also imposed an additional delay of 6 minutes before a new instance could start serving requests in an attempt to emulating what could happen in a real production environment, where setting up new resources might take a non-negligible amount of time. During our test runs, we generated traffic on the system using Distwalk, an open source distributed processing emulation tool developed by us. Such tool consists in a server module that is started at boot on each instance and waits for TCP requests, and a client module that submits requests to the load balancer with the aim of increasing the CPU utilization of the instances. The client was configured such that it spawned 6 threads, each one provided with a trace reporting the operation rates in terms of requests per second, that should be maintained for an interval of 1 minute each. The trace was designed such that the resulting CPU usage of the VMs resembled the B pattern in the figure. Each thread was also forced to break its work in 1,000 sessions, such that a new session opened a new connection with the load balancer that in turn selected a possibly different target distance. The experiments were carried out using an only one deployment of OpenStack, Victoria Release, deployed using the tools provided by Colla. Notice that in this case, the various OpenStack services are installed and operated within several Docker containers, not on bare metal. For completeness, I reported here also the specs of the server that hosted the OpenStack deployment. In the CPU usage plots, the one at the top, the blue curve represents the ideal workload to be submitted by each thread of the distort client to the load balancer. Since we have 6 threads and initially only 2 VMs, this results in each VM handling the load of 3 threads, as highlighted by the other curves. As visible, the standard threshold-based scaling strategy fails to scale up the cluster on time, as we need 3 consecutive violations of the thresholds in order to start the scale-out operation. Additionally, the start time of the new VMs takes as much as 6 minutes. Therefore, the scale-out decision happens approximately at minute 73. However, the new VMs start serving requests only approximately at minute 83, after the cluster has been overloaded for about 8 minutes at full CPU utilization. Indeed, observing the obtained client-side response times in the plot at the bottom, we can see that this resulted in a heavy degradation of the performance, with response times going up to more than 100 milliseconds. On the right, you can see the results related to the predictive policy that leverage on a linear regressor. Here, the red curve highlights the predicted average CPU utilization for the whole cluster, assuming the size of the cluster to remain constant. The simple linear regression-based prediction policy performs a better job at predicting the growth of the CPU utilization on time. Indeed, it activates the scale-out earlier, approximately at minute 65. The anticipated scaling has also a clear effect on the observed client-side response times, which stay all below 4 milliseconds. Here we can see the effects of using a simple MLP and RNN respectively as predictors. In these cases, we can make a similar observation about the benefits of the anticipated scaling, as it was the case for the linear regressor. However, with respect to the linear regressor, the neural networks-based approaches manage to capture the nonlinear behavior of the input RAM, which exhibits a clear upwards curvature. Therefore, they scale even slightly earlier, approximately at minute 60. For instance, the MLP-based policy results in slightly better response times in the worst case during the considered time frame. However, overall, all considered predictive solutions perform similarly from the viewpoint of the client-side performance. For completeness, the top table reports the average and various percentile values of the response times observed by the client during the time window shown in the previous picture. As you can see, all predictive approaches obtain comparable performances from the client perspective, in contrast to static policy that exhibits heavy degradation in its ability to serve requests. Additionally, the bottom table reports the average overhead imposed by the proposed forecasting component at each activation, that in our experiments occurred once per minute. Notice that the total time also includes the overhead imposed by interacting with OpenStack APIs for authentication, fetching input data, and so on. So, in conclusion, in this work we proposed a general framework to enable predictive cloud operations based on monitoring metrics forecasts. In particular, we used this framework to realize the predictive auto-scaling mechanism that is compatible with the OpenStack ecosystem and that leverages in particular on the tremendous monitoring capabilities offered by Monasca. We released our forecasting component implementation as an open source project, namely Monasca Predictor, and you can also find on my GitHub all the material required to reproduce the results that I showed in this talk. In any case, any kind of contribution or feedback is more than welcome. Feel free to head over to the GitHub repos and open issues, or get in touch with me directly to discuss. For what concerns future works, we are planning to improve our implementation by integrating it further with OpenStack to provide operation teams with other useful data-driven tools. In this sense, one possible extension of this work might be implementing more complex scaling policies with respect to the threshold-based ones. For instance, an interesting idea is to explore the effectiveness of reinforcement learning in this scenario. Also, another important challenge is to carefully address models retraining to counteract the effects of concept drift. Finally, we plan to conduct a more thorough validation using data coming from real production environments. That's all from my side. Thank you very much for attending this talk. I'll be very glad now to answer your questions and receive your feedbacks.